Can you read what is written here on the top? What is it first line and say? Is interaction critical? So this is about how do you choose different types of models, and this tree helps you to drive. It's not like every time you choose SIR type model. There are different types of models. So for example, is it interaction critical? Interaction means, what does interaction mean? If it is about influence, it is about infection, it is about contacts, then that's an interaction. So answer is yes and no, then you look for other things. So for example, yes, then need to model individuals, whether you want to model individuals or you model basically non-individual. If it is no individual, then you take SIR type model, maybe system dynamics model. If you are individual, then discrete event simulations, micro simulation, agent-based model. These are the three types of models, by the way. And so on and so forth. Events, there are certain events that you capture, like treatment is an event, diagnosis is an event. So those type of events, if you are capturing and they are occurring on a regular interval, then you take care of it based on decision tree. How many of you have heard of decision trees? So it is not one size fit all. You know what is one size fit all means? What does one size fit all means? That means I learned disease model, SIR model, and I use that model everywhere. No, it doesn't work like that. You have to look at what is needed in your research question that guides you which model to use. So decision tree is a very simple model. It's a tree, bifurcation. And then there are Markov model is require health states. If there are states also, and if it is not interaction is needed, then you use Markov models, simple Markov models. Have you anyone used Markov models? It's also having a compartment. For oncology, for diabetes, you use Markov models, not infectious disease model, not SIR type model. Why? Because there is no interaction important there, right? The people get the disease due to social factors, due to genetic factors, not by interaction, right? So that's where the Markov model comes in. Individual sampling model is another type of model. So this tree helps you decide what is the model that you will use in your work. These are the most important softwares that I use to do the modeling work. NetLogo. How many of you know about NetLogo? Have anyone used agent-based models in the work? Okay. How did you use it? Which software?
Make.com.
Huh?
AI agent models.
AI agent model, okay. But these are the already inbuilt packages that you can use, software that you can use to generate models. It's called NetLogo, and there is another software called as AnyLogic. MATLAB, all of you might be aware of MATLAB, right? MATLAB is another. Now Berkeley Madonna is also another software that is very easy. It's a drag and drop. It has circles and you drag it to make a box compartment susceptible. And it has arrows, you drag it, and it has very cool features. So you are not spending time in drawing and writing down the equations. It's saving a lot of time actually. Also RStudio, R you are using it, right? R Python, yeah, you are using R, okay? Python? Yeah, Python, you can use that. C, C++, these are high programming languages that you can use. What is Shiny? Have you heard of Shiny?
It is an integrative app built under R.
Yeah, but why is it used? Why is it used? What is the purpose of Shiny? Anyone? Have you heard of Tableau?
Yes, sir.
Have you heard of Power BI?
Yes, sir.
Okay. These are for visualization, better visualization software. Right? These are specific visualization software. R Shiny is one of the package of the R. R is a programming language that gives features for visualization of your model simulation. Okay, so that is what we use it. So this is a model that is being used by CDC, Center for Disease Control US. Basically, it is mapping the infection of a different type of disease and its curve over time. It is mapping something else. You can enter certain inputs here. So it's a beautiful, easy to work with the models once the model is made. And it is made in one of these softwares like Tableau, Power BI, R Shiny. Python also have something, right, similar to that. Okay, but these are common ones in business. Now AI tools are also coming into pictures, but I don't know which one you people are using nowadays. Okay, so this is this thing. I have few things more, but what I want to do is, let's see. I want to right now talk about this thing, but before we go further, you have seen some examples of the projects in the slides, right? You saw the examples in the previous slides, right? Now you are ready to think about your own group projects. Right? You have better idea. And he was mentioning about few projects in the morning. So where is the sheet? Where is the sheet? I think we were circulating some sheets with the names. We are lost. Where is the sheet gone? It has to be here only. Did you guys pass it back? Yeah? So who was the last one to sign or who did not sign it? Oh, it's in the folder. Okay, everyone signed it in this? Is it there? Okay, we have lost a sheet actually. Is Ashwini have it?
Yes, sir. Yes, sir.
Ashwini have it? Okay. Okay, we'll get it. So we'll take a break after the, before we start in the lunchtime. After the lunchtime, and we will try to take 15 minutes to think about a research project title, and we can discuss in the evening about it. Okay, so now what you have seen so far is how is the model look like. You want to now do analysis, mathematical analysis, or you want to look at the simulation of the model? Where is Ashwini right now, Ron? Can you call Ashwini, please? Can you message him? If you want to work, so there's two choices. We can start with some mathematical analysis first, or we can start with some simple simulations. What do you?
Some mathematical analysis.
Say again? Okay, how many in favor of mathematical analysis? Okay, how many in favor of simulations? Only 2, 3. Okay, so I think the simulation mathematical analysis wins. Ashwini, where is the sheet? There was a signing sheet for the project. Do we know where it is? Who has not signed it for the project, group project? But so everyone else signed it, so it came this way then. It traveled this way, right? It traveled this way. Did you all remember to pass it? Right? You went it back. So what happened? You guys signed it. and gave it to who? Or you gave it in front, and they are saying they sent it back. Oh, sheet is here. Oh, it was. Everyone has his name here in the sheet? Yes? You both don't have it. So, well, you will be mentors for some of these teams. So, I think the project topic should come from you all rather than me assigning it. Okay, so decide on a project topic that interests you. For example, he's talking about latest affairs, current affairs topics, which is quite reasonable, right? As far as research, precise research objective is concerned, we all will help you in that. So it will not be random just. It will be a significant research objective questions that will be worth publishing it in a journal. Okay, so we'll continue with the mathematical analysis. So again, we are not going into very high level bifurcation analysis. We want to get a flavor of it. It's not a mathematics course. It's a course on data driven aspects, thinking process to change on the model. Okay, so this is the model that we have before, but yeah, it has some simulations also. But so basically, you have this is fitting. This is simple models and fitting a 1978 influenza epidemic in boarding school in England. Now, why did we use this outbreak? You know, it's very difficult to model, to get a data for the model. Why? Because if you are modeling, let's say, a whole nation, you know, there are people moving out of the nation, they are coming in of the nation also. So you have to model immigration and emigration also, which is very, very challenging. It becomes very challenging to get the data on that. So this is using boarding school data. What is the boarding school does? You cannot go out, right? It's restricted. So that's why this data is very good to get an understanding about the model. So basically, it uses, there were 763, it's a boys' school, boarding school, and 763 boys, and one of the boy came back from winter break with the flu-like symptoms. And they wanted to see how many people will get infected, how many boys will get infected. So, and they basically ran similar. So initial condition was everyone susceptible except one person, right? And they calculated these assays. So how did they calculate it? Well, they ran a reference point from the literature, and they wanted to see which one. They choose different betas in these ranges. They use different gammas, beta and gamma combination in these ranges. And for fixed value of beta and gamma, you can run one outbreak, right? So in order for this model to simulate, you need one value of beta, one value of gamma, and initial condition. That's it. So if you give one beta and one gamma, you will get one curve. Right? That was what we saw in the previous slide. So we used so MATLAB basically we described we had this data. Data looks like this. So first day there was the person who came from outside, the one boy that was infected. But after one day there were 3 people infected. 3 boys were infected. After second day, 6 boys, and so on and so forth. So epidemic peaked around this 8th day. And within 15 days, the epidemic is over. So the way to in the MATLAB that we simulated, we estimate the model and we get the data, is first we have to describe the function for the system, the equations. Remember the model that we have, these equations. You have to write in the MATLAB. So this is the system, which is SIR is the system equation. So beta and gamma are parameters, and S I and R are the compartments. So these are the three equations: minus beta Si plus beta Si and minus gamma I plus gamma I. Beta Si, gamma I and gamma I here. So those are the things are defined in this this is differential equation. This is a differential equation and this is a system. And then you have the data. The data is stored in for different days in an array form for different time points. 14 days. It took 14 days for initial condition. In fact, one came and the first day there were 3 infected. So we take the first day as infection. 63 were the boys total, 3 infected and remaining this thing. So this is the initial condition. Y0 is equal to 760 is the susceptible, infected is 3 and 0 is recovered. And then we simulate it. Simulating, we are using a function called a OD45. How many of you have used MATLAB? Okay, let me ask a different question. How many of you have not used the MATLAB?
I have basics idea.
Yeah, basic idea you have, right? So almost all of you guys. So basically this function is important here. To run this function is calling this SIR function. See, this is the SIR function. This is being called by OD45. OD45 is an inbuilt function that is solving the SIR system. And then you plot the model. So basically, this is what is being done: data, model, and simulating of the model. Now, in order to simulate the model, where is the simulation happening? This is the simulating of R. You are computing for initial conditions and for the parameters P0. P0 is, where is P0? Sorry, P. P is beta and gamma. These are P basically. What are you saying? I didn't get you. Anyone saying something? So this is the initial value. Beta is this and gamma is that. That goes in an input for the parameters. Y0 is initial condition. T span is the time. Different time we are taking 1 to 14. And T final, this time is same as T span. That is T span. And SIR is the function. Here is the function. So this simulates for one fixed beta and one fixed gamma. This function simulates. And the next is the plotting. Okay, but this is done only for one value of beta and one value of gamma. Now what we want to do is estimate what is the right beta and what is the right gamma that gives me that data that we have obtained. Remember, the data looks like what? Data is this, right? This is coming from the hospitals in the boarding school. First day these many patients. Second day that many patients, so on and so forth, right? So now we are in, so once this model is working with the one fixed beta and gamma, that beta and gamma we don't know yet, right? It is just arbitrary value of beta and arbitrary value of gamma. This whole thing can simulate. But now we want to know exact beta and exact gamma that will actually capture the data set. I want the data set to be captured by that model. So that's where this function starts to come into picture, residual and optimization. So I'm using this as a new function now, which is basically finding, you see it is calculating residuals. I minus I data. I from the model and I data from the actual data. So this difference is the residual. Is that making sense? Yes, no? Do you know what is residuals? Right? So this is the residuals. Basically it shows the difference from, this is the data, and the model is, so for fixed value of beta and gamma, it is plotting one curve. It is plotting one curve. So it is looking at the residuals of those data points and the curve. What does that residuals look like, right? And that is what is computed here. And so this is a function that computes the residuals given one curve. One curve and the data gives you the residuals. Now what this another function which is called LSQ and non-lin is the inbuilt function in MATLAB, which is optimizing. And basically what it does is, it takes this function and run it for different beta in this range. It takes, now it randomly sample one beta, randomly sample one gamma, and for that combination of beta and gamma, I simulate one curve and find the residual. Then it takes one more beta and one more gamma, it plots one more curve and compute the residual, right? And then it finds the minimal residuals compare of beta and gamma, right? Does that make sense or no? There's no board here also. So anyway, so it's basically optimizing this thing, and it is finding which beta and gamma will give you the lowest residual, good fit to the curve. Is that what you guys have done before? Any one of you? Optimization of the. So basically, this is how we do it for the for finding the parameter, right? Parameter combination, because we want to know what is my beta and what is my gamma that will fit the data. That will fit the data. So that is what will spit out to me. I will share this codes with you, so you will have that one. But this is how we know exact beta and gamma. There's an assignment here where you have a data for a different disease, and there is some work that you can do it with that. But again, this slide is with you. You can always do. So this is the goal for most of the work. In most of the work, what we do is we build a model. We have to then find the right combinations of the parameters that will result in the data set that you have in hand. Now, this is a simple model, but you could have more complex models, but the process remains the same. Okay. So next we go to the analysis of the model, mathematical analysis. So basically what we look at is an asymptotic solutions, and which are equilibrium solutions. Do you all know about equilibrium solutions? All of you? Has anyone not heard of equilibrium solutions? Everyone? Okay. So then basically you find the null lines, you set it equal to 0, right? And you solve for equilibrium points. Do you know how to solve it, or should I continue, or should I spend more time in this? You all know, right? So this is an example of SSIS model. And basically this is used in gonorrhea, it is used in other disease of similar top, where you are in fact, as soon as you recover, you become susceptible again. Gonorrhea is a sexual disease, by the way. So, but there are other diseases also where you recover and you become susceptible immediately. There is no recovery stage here. So this is the model for that. You recover, where is your recovering happening? Yeah, I gamma, and you go to plus I gamma here. And there is people dying also, and getting births also in this model. So how do we find equilibrium solution? You set it equal to 0, and then you find equilibrium solutions, right? You set it equal to 0 and you isolate S and I. So there are two solutions. There are one disease-free solutions, which is I0, S0, and the other one is endemic solution, which is looks like this. I is this one. Is that okay? This is making sense or no? Right? So, is this solution always exist? Check the existence, right? Existence is, this has to be, because we are talking about disease, right? Disease cannot be, number of count of cases cannot be negative. So this has to be positive. So beta has to be greater than this thing. Beta has to be greater than this thing in order for this endemic state to exist. Okay, and basically this is an R0. This is one way of computing an R0. This is not the only way, but this. So there are two equilibrium. One when I is 0, and the other one when I is this, and this condition holds. Okay, these two are the equilibrium solutions. One is a disease-free equilibrium solution and one is an endemic equilibrium solution. SIR model the same way. You set it equal to 0 and then you compute it, you get endemic labels like this, and the criteria for existence is this term has to be greater than 1 in order for I to be positive. Right? Now, have you who has calculated R naught before? Reproduction number for a model? You have? How many of you have? Let me see the raise of hands. Reproduction number, how many of you have calculated? Okay, so all of you, I mean, a lot of people have calculated. So basically, the next generation operators is a way of calculating the reproduction number. So what it does is basically separates the system into nuke infections and just the rate of transitions. And then it computes at the disease-free states two matrices, F and V, and therefore, and then R naught is a dominant eigenvalue of F times V inverse, F times V inverse, and dominant eigenvalue of this product to compute an R naught. Okay, so let's see how we will compute. So suppose this is a model, S, E, I, and R, and this is the equation of the models look like. Right? Writing down equations is not difficult. It's just knowing the rates and writing down plus minus appropriately in terms of the equations, in terms of the compartment. And then you set it equal, you basically compute F and V inverse. F and V inverse. So what is the new infection here? What is the new infection? Is this one. This is a new infection. And this is the only new infection. This is an old infection going from one state to another. This is an old infection going from one state to another. But these are not new infections. So only beta SI is a new infection. So it's basically beta term is the new infection. Rest. So why is it 2 by 2, not 4 by 4? You could have 4 by 4, but only taking infected compartment. This is only taking infected. Which are infected compartments? Susceptible? E and I is. So R is not an infected compartment, right? It's a recovered. People have recovered from the infection. They are not infected. So only these two equations are important in the reproduction number. E and I. E is people who are infected, exposed basically, but not infectious, and I is the people who are infectious, right? So you only take E and I equation and you look for terms having new infection, and only this beta SI is a new infection, which is right here, and then rest of the terms are here. Kappa mu is here, and then this kappa is here. And then basically E, because it's a E coefficients on this line, and I coefficient on this line, basically. So there is no I in this equation, and there is no I in this equation because this term is going in this F matrix. Okay, I'll show you another example, but just a quick glance of it. This F and V is easy to find. This is a transition matrix of infection. This is a new infection, basically. So R naught is computed by calculating the product of, you take a V inverse of that. By the way, before that, you are taking partial derivatives with respect to E, D of this equations by E, and at x0 stands for equilibrium, disease-free equilibrium, which is 0, 0. In this case, 0, 0 is a disease-free state. And then basically, then you compute F and V at a disease-free state, and then you compute F times V inverse. You have to take V inverse, you will get F times V inverse as a G matrix, and then you compute the dominant eigenvalue, which is what it is mentioned here. So this is very, very simple to work with. but if you follow these 3 steps, there are these 3 steps. Let me see if I have it somewhere else to compute this thing. Does that make sense? So this is, if this is a system, SIR system, we want to compute an SI reproduction number for that, then we follow the same step. So we rearrange the system so that X is an infected state and Y is an uninfected classes. So first you rearrange it, and then you only take X. This is the X is the infected compartment, and then you calculate F and V from there. So it is computed at disease-free equilibrium usually. Disease-free equilibrium you have to compute from the model, and it will look like third step. So this is 1, 2. Third step is computing F and V matrix, and then therefore basically you will find F and V in the fourth step. F is the partial derivative with respect to the disease state at the disease-free equilibrium. The product is called as the next generation matrix, FV inverse. So let's see what is this thing. So for example, F and V in this case is these are the two. This is the only infected compartment. Only infected compartment. So F consists of new infection, which is this, and rest of the terms goes in the V. Right? And so di by dt is only infected equation, which is F vector times V vector here, and then F. This is script F and the script V, and this is F, capital F and capital V, which is partial derivative with respect to I at the disease-free state, and the this is also a derivative with respect to I at a disease-free state, and that will give you F and V. And inverse of this is 1 over mu over gamma, so beta times 1 over mu over gamma, which is FV inverse. And that, in this case, it is 1 by 1. So your R naught is this beta over mu plus gamma. If we, okay, so this is what the calculation look like. If you redo the calculation, now here, this is SEIR model, you have an exposed class, right? And this is an infected class. And so now you will have F as a new infection. Is that the way you have done it, or you have done it in a different way? Same way, right? But this is a common way to do the next generation matrix. It has exposed and infected compartments basically, and then you compute F from the script F, and from script V matrix, and then compute the V inverse and the FV inverse product, and that's the eigenvalue, dominant eigenvalue of this is R naught. Okay, for this one, disease-free equilibrium was, for this model, the disease-free equilibrium was this. How do you compute? The way we showed, setting equal to 0 and finding the disease-free equilibrium. This is a model with SIS with 2 strains. There are 2 strains, I1 and I2. Susceptible, I1 and I2, there are 2 strains of the disease. And they are interacting with the 2 strains are infecting. So the susceptible can get infected with the first strain and the second strain. And the different strain have a separate equations. So same thing, you calculate script F. So there's 2 infected compartment, I1 and I2. So this is script F and this is script V. New infection in script F and all other transition in the V matrix. And then you compute at disease-free the partial derivative with respect to each of the infected compartment, which is I1 and I2, and that will give you F, and similarly V matrix, and you compute inverse of V, and then you have basically F times V inverse, which is next generation matrix, and there is basically the dominant eigenvalue of this, which will be maximum of these two. Right? These two are the eigenvalue because this is a diagonal matrix. So this is the R naught. What it is saying is it depends on which strain is more dominant, and because it's saying maximum of that ratio, and depending on that the disease will propagate or not propagate. So this is for the two strain model. This is a model for computing R naught for TB with the exogenous reinfections, and this is basically people who exposed are also getting infected in this, so I is infecting E. I is infecting E. That means there is a dormant state. TB has a very special type of dynamics. The patients remain dormant. They have infected, but their infection remain dormant. They are not infectious. But once they come in contact with the infectious person, they become infectious. That makes sense? So that's an exogenous reinfection, it is called. Okay, this happens in TB, and therefore, this term is here where I is infecting E. Can you see that? Right? So this is natural term where I is infecting S people, and they are moving from here to here. Right? So this is very common in TB and this type of model. Same way, you have to compute script F, script V. You have to compute disease-free equilibrium, then you find partial derivative, you take V inverse, F V inverse. By the way, how do you find these things? With the hand or with some software? Hand, you can definitely do it, but has anyone used symbolic computing? Do you know what is symbolic computing? MATLAB. So MATLAB has a package called Symboice. What is it? Okay, but so all the these programming language has packages in it that can do symbolic computing. What is symbolic computing? Right. So instead of giving a numerical values, we are using Greek letters, and we are asking it to find inverse. We are finding inverse, we are finding product of the matrices without giving numerical values of these Greek letters, right? So those are symbols you are using to compute the calculation, mathematical calculation. That can be done by the many, Maple does it, Mathematica does it, right? MATLAB does it, Python does it, R also has a packages like that. So we do symbolic computing because it speeds up the process of mathematical calculation. And therefore, and then eigenvalues becomes very difficult once it is maybe 4 by 4 matrix. It is very difficult to compute eigenvalues. In that case, symbolic computing helps a lot. Now, if it is very complicated, the symbolic computing may not work very easily. Anyway, so let's just stop here actually in this one, and we will do some simulations actually. So can we share the files in the Dropbox or in the Google folder?
Yes, sir.
Yeah? Okay. So I'll send it to you. Can you share? Okay, how many of you have Excel in your computers? You have computer right now? No. Yes, no?
Yes.
Okay, let's take out our computers. We'll work on this thing right now. Let's take out our computers. We'll work for the next few minutes. But how will you share the, can you share the Dropbox link or the Google Drive links in the in the group? So he's sharing the Google Drive link where you will see all the lecture notes as well as the file, programming files. Oh yes, they will need the internet, right? How will they download it?
For internet connection, they have to log in with the institute ID, but they don't have access for that.
Right, so how do they do?
They can use their mobile.
But on this spot you have to use your sorry guys. So, yes, I mean somehow you have to get that file on your laptop because then only you can work with that file that I have shared with him. Have you shared? So he has already shared the link on the WhatsApp group. Go to there and download that file on your laptop. got the file? Yes. All of you? Anyone is still trying to get it? Oh, Can you help everyone? Can you guys see that if they are facing problems, are they got the file or not? If you have got the file, open the file. Open the file simulate model SEIR. Simulate model SEIR. Now I am intentionally using the Excel. I know you all have experts in advanced languages like R, like Python, right? But I'm intentionally doing this thing in Excel. There's two reasons for that. One is, of course, the conceptual interaction with the terms, how that works. And second is because in industry, people don't use very simple things, they use it in industry. Excel is used almost 80% of the time. 80% of the time. So you should be aware of it. You will say you know Excel, but I would say there is a lot of things to learn in Excel. I'll show you an example. Okay, so everyone got it? Anyone is still trying to get it? If not, try to look into your neighbor's computer if you have somehow not able to get it. So the goal of this is to set up a model, epidemic model. How do you set up? And the second is to simulate that epidemic. So if you see here, there are input model parameters, there are total population size. It's basically doing SEIR, susceptible, exposed, infected, recovered. So that's where it is basically average infectious pre-exposed period, average duration of infectious period, and this is the reproduction numbers, total population size. There is effective contacts, which is leading to beta, and this is infectious rate, and this is recovery rate. And these are initial number of susceptible, initial number of exposed, initial number of infectious, and recovered. So these are all inputs of the model. Okay. Now what is this thing here? Cell names. What are these things? Has anyone know what is cell names are? How many of you have worked on Excel before? Everyone? I'm guessing everyone has worked on Excel. What is cell names? Have you used cell names? Anyone has used cell names? If you have used, you look at this corner here. You look at this corner. Can you see that here? In this corner. This is called cell names. I am naming this cell. This cell is F9 cell as T steps. This is the name of this cell. Okay, and then the cell name of this cell is total population. Now this cell is not named. For example, I am not naming anything here. This is not named. You see that? Only this once I am naming it. And these are the names of the cells basically. I mean, this is for my reference. This is my reference, but this is the names are given right here. You go to the formulas. In the formulas, there is name manager. There is a name manager. If you click that, you can see all the cells that are named by me. All the cells that are named by me. It's one of the efficient way of doing programming in Excel by naming the cell. So these cells are named here, and I'll show you the benefit of naming in few seconds. So this is all the inputs. There is a figure, you don't see anything else, but as soon as you start working on it, you will start seeing the figure going to generate something. So this is susceptible, this is exposed, infectious, and immune is the recovered compartment. Okay. Initial conditions are in yellow, 0 time step, there is the initial, there is everyone, there is 100,000 people, all of them susceptible except one infectious at the time 0. And immune and exposed are 0. How do you compute this? Look at the formula here. It is computing B54, which is this initial value, is discretizing the differential equation basically. And then beta S, this is S at the previous time, this is beta S at a previous time, and then infected number of people at a previous time, beta Si. This is beta Si. And what is beta? What is beta? No, but I have named it. This is the name of the cells is beta. Name of the cell is beta here, right? So this is this thing here, right here. And then this part is for the exposed. It is the number of exposed at the previous time, which is this one, plus how many new cases have been come to the exposed compartment, and how many people recovered, minus how many people recovered. Is that okay? Is it making sense or no? Right? Very simple in this way. And recovered is the same way. Previous time step, how many people were there in infectious, how many new infectious have come from E compartment, and how many have recovered from the I to R. By the way, there is an exposed compartment, so there is no recovery here. This is people going from E compartment to I compartment, basically is this one. Is that okay? It's a discretization basically. So what we do is, this is a model. Now what we do is, now if you see here, it is adding time step. And again, 1 day is a time step. You could have 20 days, you could have monthly, for example, 30 days. So you can define what is the time in which you want to increment your model. So here I am implementing it just 1 day. But time step is right there in the previous. Time step is here. This is time step. Right? This cell is a time step. I could make it 30 days increment rather than 1 day. Okay, so where is the model? So here is the model. So what I will do is, I will run it for, let's say, 100 days. This is 100 days, right? Now, if I click this box here at the corner, I would have all 100 days number of susceptibles. If I click this box, this corner, it will fill up for 100 days. If I click this corner, it will fill up for this 100 days. Is that okay? So this is filled up the number of cases for each of these compartments. And if you look at it, it is now plotting the 100 days curve. Okay. So if I continue this further and extend this thing for, let's say, actually it is not for 100 days, it is 100 rows, but it is for 45 days only. So let's say if I ran it for 200 days. Let's say 230 days. Look at this curve here. And what happened to the I1? Somehow I messed up the I. What? Okay, somehow it is messed up that I am not seeing the I compartment. So I have to check for it. But you see, it is plotting now the susceptible and recovered for 230 days. Right? It's very simple to work with like this in Excel. I work in an industry called as health economics. All the model we do it in Excel. All of them. Why? Why do we do all the model in Excel? If you go to the industry, there is more likely that you will end up doing Excel. Why do you do in all? I mean, I have done in high performance computing also, but that's not the purpose. Why do we do, industry do it in Excel? Can you give me a reasoning? Well, they have money, they can get subscription for anything different. So money is not an issue. So what do you think, why do they do it?
Large audience.
What does that mean?
Like people are more familiar with Excel now.
Okay, that's a good point, but who people you are talking about?
People in the industry.
So mostly in industries like big giants, Google, Microsoft, data analysts and data scientists, they work on Excel. So maybe they can share some of their data and they can work and do modeling and prediction and prediction.
Correct. The reason is partly both of you guys. There is more people know it, Excel. In fact, all of them knows it. So it's a common standard knowledge for across. But not only that, their customer who are not mathematicians, who are maybe in medical fields like clinicians, they don't know programming. At least the level of the programming that we do it on when we do the modeling. So how will they know? They would know things in Excel very well. So to pass on, to share these models with them, they have to do it in Excel. So it is an easy way of sharing the modeling work with other folks. And that's why the industry will always use Excel and will use it for next many years. So you have to be intelligent also, because sometimes when we are in a graduate school, we think, oh, we will do very complex mathematical analysis and we will do a lot of high complex programming, and that's how we'll build my career. That's not the fact. That's a myth. You know what is myth? It's a wrong understanding. Actually, you have to do things, you have to become expert in the things that is sellable. And you know, only 10 to 15% of the people goes in academics, even if you do PhD in mathematics. I mean PhD in that area. Not everyone will become faculty. 10 to 15, that's the statistics I am talking about. So where do other people go? They are not unemployed, they are earning something, they are going in private sector. Right? You understand my point, what I am trying to say? It's very important, relevant features that I am saying. In Excel, there are lots more features that you guys have never heard about. And we do it. Macros, we use macros also here in industry. You know, I was not into Excel until I came to the industry, and then I have to learn it myself. And there's a lot of struggle in that type of. I mean, you ask me to do C++, I used to do things in C++, because it is easy to run on the high performance clusters. It is easy to send the code. Not an Excel model will not be very good for that. Now again, having said that, if the model is too complex, in industry by the way, the models are simple. Because they don't like complex models. They like simple models that could be understandable, explainable to the clients. So these are the models that we see it, and also you can make it visualizations like as you do it in Power BI and Tableau. They are good for visualization. Excel you can do visualization. And you can share this file easily. You cannot do it in R. Why cannot you share in the R? Why cannot you share in the R? You need a license for R Shiny, hosting of R Shiny app somewhere to share it with someone. That's a lot of challenge, practical challenge in real life. Until unless that other person has a license for R Shiny host, you cannot share it. And same thing with the Python. Again, Python, the issue is people have to know that sophisticated language in order to run that. So there are practical challenges which makes it very limited to go. Okay, now do one thing. Can you count what is this thing? Now the next step is, how do you compute this and this? What is this thing? Newly infectious person. How many newly infectious person is there? It's basically these are the newly infectious. Okay, where is this coming from? Well, it is this thing. These are the people coming from E to I. These are the people who are coming from E to I, right? E to I. Those are newly infectious people, which is E to I. Is this only this term? You can see that, right? So this is this thing. What are these newly infected people? How do you compute this? How do you compute this?
Infected of the previous versus the new one.
Correct. From here.
In first case it will be
This one. Right? It is this one. Now you do this thing. I'm sorry, I copied wrong actually. I copied it this one. So this is this one. So these are the count of newly infected at different time points. And these are newly infected and newly infectious. Those are two different ones. Okay. What is the total population? Is anyone leaking this from this population? No one is leaking out. So this is basically equal to sum of susceptible, infected, exposed, infectious, recovered, which is 100,000, right? And if you see, every row will be 100,000. Come on. Why is it not coming? They are all 100,000. Is that okay? And that is what it is being found. Number of new infectious cases is being plotted. Now open this other file. Now open this other file, which is compare. This other file, if you open, and you have all the formulas that are here. These are all the formulas there in this thing and calculated this part. This is SCIR model. same thing you can do it for SIR model. Same thing. And there is a formula for SIR model. Right? And now here is the second figure in this, which is comparing SEIR with SIR. Recovered compartment look like what? And infectious compartment look like what? So what do you see here? What do you see in this? What do you see the difference in the two models, simulations, SEIR and SIR? What can we learn from it? What are we learning from the difference in the solution of SEIR and SIR? One has an exposed class, one doesn't have an exposed
The
class.
exposed time gives time for the curve to like. See in the non-SER standalone SER model there is no exposed class. Exposed class of the time is time is less. So exposed class is actually increasing the time. That's why the
Yeah, so there is a delay. There is a delay in people getting to an infectious class. Right now, they are holding up people in the E compartment, right? So, and in the E compartment, they are not infecting, right? They are infected but not infecting. That's the definition of E compartment, right? So that is why what you are seeing here in that this delay in the infectious compartment is causing a smaller peak and shifting to the right in the SEIR compartment as compared to the SIR compartment. It's delaying the E compartment is delaying the infection process, and therefore it is lower outbreak and shifted to the right. And that's the important thing. And what you are seeing in the recovered compartment is that SIR people are recovering faster and to a saturating it quicker than in a SEIR compartment. Okay, so this is very important for you guys to think about it. We will do R and MATLAB at some point of time in the course. At least what I will do is I will just share the code with you guys. What we will do now is, this is all we will do it in this simulation, in this one Excel simulation. But what we will do now is we will talk about the projects. And we have, how many minutes we have for, what is the time right now?
8 minutes.
10 minutes almost. We have 10 minutes to the lunch time. So what we want to do is discuss about topics. So anyone has an idea about what they want to work on? And we can discuss and we can think about who wants to work in that. Where is that sheet? Signing in sheet. Okay, group 1. Group A, Vivek, Gopal, Anjali, and I can't read the last name. I mean, eyesight is getting Shubham. I think Shubham. Four people only. And the first one only 4. Okay, fine. That's fine. We will move around. What do you guys are interested in? What type of problems? I'm asking these 4 folks. Where are these folks? Vivek, Gopal, Anjali, and Shubham. Okay. So you guys are sitting very far from each other, but what do you think? What is your interest? What type of research you, I mean, for example, in the morning he was talking about Aravalli range and like he was all over the place, by the way, but he did showed some interest in environmental related issues. What about you?
So we discussed that.
But what is your interest, I'm asking?
So my interest in tumors.
In tumor?
Yes, sir.
Okay. Okay, you want to think about tumor, which is fine also, which is okay. So something to do. So you have to think about what is the challenge about tumor that you want. Because tumor is a big Big area, right? So, okay, what about Anjali? You are Anjali?
Yes.
So what is your interest? Is tumor is interesting for you? Yeah? Okay, so think about something. Now also it may not be infectious until unless you are talking about HPV. You know what is HPV? No. It's HPV, sorry, I'm saying HPV. It's a virus. It's a virus that leads eventually to one type of cancer. Okay, so that's where the role of HPV. Look at the HPV. That could be infectious process, and it's important thing is a vaccine. So you have to read and think about what are the topics. Who is the other person? Vivek, where is Vivek? Vivek, what is your interest? Okay, that homework was yesterday. So talking. Okay, so what we will do is after lunch, we will probably sit for half an hour in our group, this group. And we want to know what is few topics. You can have plan A and plan B, right? To think about what would be worthwhile for you all as a consensus. Not that I am interested in doing that. If that is the case, that is also okay. We will look for other people who wants to work in that area, right? We can always move around groups. But we want to finalize the group by afternoon, right? So that we can do some things by the end of the. So we will present also in the last class what we have achieved. I mean, I don't expect everything to be done, but at least you should be having a concrete objective, research objective, and also some model framework, some model equations that we can achieve it definitely. Okay, and we can assign mentors that we can meet it on a long-term basis remotely. Okay, so we'll stop here. What is it's 1 o'clock right now, and we will. How long is the break? 1 hour. So do you guys have to walk back, or where is your lunch? In mess, which is the next building, so not too far. It's far. So that's good in digestion also.
Yeah.
It's always a cross. Oh, they are in the bus. Okay, that's fine. So let's stop here and we will continue.